Good morning, everybody. I am Leonardo Castellanos from the Advanced Laser Diagnostics and Flames Laboratory of Delft University of Technology, and my colleague Francesco Mazza and Professor Alexis Bohlin from Luleå University of Technology in Sweden have been working on the development of a novel detection strategy to measure water vapor in flames by using time-resolved coherent anti-stock Raman scattering spectroscopy, or as we simply call it, CARS. So CARS is an extremely important tool for combustion diagnostics that allows in situ non-intrusive measurements of temperature and also multi-species detection with excellent precision and accuracy. However, a recognized challenge for combustion diagnostics, and in particular for CARS, is to measure accurately the concentration of water vapor in flames. Since water is a very important scalar to be measured in various applications, and in particular in hydrogen combustion, which is the only major product, in this work, we want to overcome this challenge of measuring water vapor in flames by using a new strategy based on time-resolved, pure-rotational, femtosecond picosecond CARS. So the great potential of pure-rotational femtosecond picosecond CARS is that we can perform simultaneously frequency and time-resolved probing of the flame, let's say, by employing ultra-short laser pulses. So you might wonder, okay, why is this relevant for combustion diagnostics? So to understand this a little bit better, let's consider the CARS signal from a nitrogen molecule, which is one of the most common species used for thermometry, as is present in the reactants, oxidizer, but also products. So in this technique, a broadband femtosecond laser pulse provides both pump and stock photons to excite the molecule of interest, created a nonlinear optical response on the medium. This response evolves in time very quickly, and actually it decays extremely fast, in orders of hundreds of picoseconds at atmospheric conditions, due to inelastic collisions between the excited molecule, which in this case is nitrogen, and other perturber molecules in the provolume that destroy the induced coherent. So this process is called collisional dephasing, and is extremely sensitive to temperature, pressure, but also it depends on the collider species. In time-resolved CARS, by using a picosecond duration probe, it is possible to minimize this dephasing, and therefore we can perform time-resolved measurements. On the other hand, this picosecond probe has a relatively narrow spectrum on time, and therefore we can resolve the CARS signal also in the frequency domain, and this is where we get the sensitivity to temperature, and also this is how we detect different combustion species. Let's see how. So here you see a typical pure-rotational CARS spectrum of nitrogen at room temperature. Each of these lines corresponds to the Raman transition between rotational states, and the envelope of the spectrum reflects the rotational Boltzmann distribution at this temperature. If we increase the temperature, we see that more rotational states are becoming populated, and it also reflects directly on the spectral envelope, which yields to a great temperature sensitivity. On the other hand, different species has different rotational energy states, so the rotational spectrum represents a unique fingerprint that allows us to identify different chemicals and to measure the relative concentration. So here is the typical rotational spectrum of room temperature air, where nitrogen, here in black, and oxygen in blue can be easily identified. So to summarize, we have high temperature sensitivity, but we have also multi-species detection capability. So what is the challenge with water vapor? Well, the pure-rotational CARS signal generated from water molecules is simply too weak to be detected in any combustion application of interest. As a matter of fact, this signal have been reported only once in literature by researchers in Lund. They use a nanosecond CARS system to measure the pure-rotational spectrum of nitrogen and water vapor in a gas cell at 400 Kelvin. What they found is that the nitrogen signal was at least 5 orders of magnitude stronger than the water vapor one, which means that it is clear that this technique will never work in a flame, let's say. So water is here, there is a spectrum somewhere down here, but it's simply too weak to be detected with this technique. Still, there is another degree of sensitivity that we can exploit, and this is the time domain. In particular, we already discussed how the collision between our nitrogen molecules and other perturber molecules cause this dephasing of the rotational coherence. In time-resolved cars, we avoid this by probing the coherence before the collisions can destroy it. But this means that we can also resolve the collisional process in time by and use it to extract information about the collisional the molecular dynamics. This approach has already been demonstrated to measure pressure, for example, across shock waves. But today, I'm going to show you how it can be employed to measure water vapor. So let's discuss a little bit more the details. So here I'm presenting the basic time domain model of the car process. So this nonlinear molecular response is basically the results of the interference of a single damp harmonics that corresponds to the Raman transition between different rotational states and resulting from all thermally populated vibrational states of all the Raman active species, here represented by the index K. Each of these Raman transitions has a damping coefficient corresponding to the collisional dephasing rate in the time domain or to the line width in the frequency domain. Here, as you can see, there is a particular, here you see the line width of nitrogen cell perturb and a comparison against the line width when water is perturbing nitrogen. So you see there are two things that are important here. One is that the magnitude of the line width is significantly larger when water is perturbing nitrogen. But also there is a non-trivial dependence on the rotational quantum number of the nitrogen molecule J. So in the case of a binary mixture of, let's say, 70% nitrogen and 30% water, this water molecule manifests its presence in the car signal by a faster dephasing rate. So what we can do is that we can employ a probe pulse at a very short probe delay to perform thermometry and to detect the species in the frequency domain, and use this and then delay this probe pulse and acquire the signal to deduce water vapor from the collisional dephase. Okay, now that we have introduced the main idea behind this technique, we can move to the proof of principle. So in this case, we use a laminar diffusion a hydrogen-nitrogen flame provided by a standard Mazza burner. And the main motivation of using this flame was that the flame front is highly stable in time, so it might reduce our uncertainties in the measurements. And basically what we did is that we performed point-wise car measurements across 25 radial locations 1 millimeter above the burner room. So here there is a sketch of our experimental setup. We use a 35 femtosecond pump stock pulses to excite the rotational coherence of the nitrogen, oxygen, and hydrogen molecules, and then we probe this molecular coherence by using a 13 pulse duration, 13 picoseconds pulse duration probe. So let's consider, for example, a point in the reaction zone of the flame when we expect the maximum temperature but also the maximum water vapor concentration. So here on the right you can see the experimental data corresponding to the integrated signal intensity at 6 probe delays up to 360 picoseconds. So the water vapor mole fraction is extracted by comparing this experimental decay to the one predicted by the time domain cars model for different concentrations of water. We performed this experiment across, we repeated this procedure for all 25 different locations, but also including the effect of collisions with hydrogen and oxygen, depending both in the fuel and oxidizer streams. Okay, so for these flames, for this particular flame, we are able to reconstruct the spatial profile of the whole set of relevant scalar fields, which are temperature, hydrogen, oxygen, but also water vapor mole fraction. So as you can see here from the figure, temperature was smoothly increasing from about 350 Kelvin at the center of the burner, here at 0, and increases up to 1600 Kelvin close to the burner rim, and then it decays much faster towards the oxidizer. Hydrogen and oxygen were measured directly from the frequency domain. And finally, we use the time domain collisional dephasing to extract information about water vapor. As you see, the water vapor is detected mostly in the reaction zone of the flame, with a maximum of 34% mole fraction, which corresponds actually to the highest temperature location. And basically, the minimum water vapor detected was approximately 3%, which tells us a little bit more about the sensitivity of this technique. Also, the precision of all these measurements was better than the uncertainty was better than 8% on all measurement locations. Okay, this simultaneous resolution of the whole set of scalar fields actually allow us to make a remarkable observation in this region, and it was preferential diffusion of hydrogen. This can be seen here because there was a significant reduction of the hydrogen mole fraction from 50 to about 40% in the face of a relatively small increment in temperature from 350 up to 600 Kelvin. In this region, we didn't detect any water vapor, and it was expected because the temperature was below the ignition point for this mixture, and it means that there was no chemical reaction. So then this hydrogen preferential diffusion was manifested because, let's say, the hydrogen in this the flame reduces because the hydrogen concentration was reduced because of mass transfer from the fuel stream towards the reaction zone. So we have demonstrated that water vapor can be measured via time-resolved cars, and this technique can be very powerful for laminar hydrogen flames where fluctuations are small enough so we can perform sequential measurements. But a technique that works only for laminar flames is hardly interesting for the majority of practical applications. What about turbulent flames, where the temperature and flow composition has very fast dynamics, and these sequential measurements are, let's say, off the table? Here, we must be able to perform our frequency and time resolve measurements in a single laser shot. So to demonstrate this capability, we choose a canonical turbulent flame, which is called the H3 flame, developed by TU Darmstadt. And basically this is a non-premixed hydrogen-air flame with a 1-to-1 ratio and a very high Reynolds number of 10,000. And similar to the laminar case, we acquired the signal across 25 radial locations at a height above the burner of 2.5 diameters. So we achieved the single shot detection by using a polarization control scheme to generate two linearly cross-polarized probe pulses, one at 30 picoseconds and the other at 250 picoseconds. Basically, the advantage here is that we were able to generate this dual probe in a collinear way, so there was an increased robustness against beam steering, and we also realized this simultaneous detection of the signal generated from each of these probe pulses by using a polarization sensitive coherent imaging spectrometer that was actually presented in the last symposium. This spectrometer uses some polarization optics to separate the two scarce signals generated for each probe in two distinct channels in the same detector. Here on the right, you can see the single-shot spectra acquired simultaneously at 250 picoseconds of nitrogen and two rotational transitions of hydrogen. So the effect of collisions in the signal can be easily seen in the shape of the nitrogen signal, but also in the magnitude. So here, finally, you can see the scatter plot of the water mole fraction versus temperature, here presented for 1200 single-shot Karst spectra acquired at the highest temperature location in the flame. This gray scale color map of each data point represent also the oxygen mole fraction. So basically this water vapor mole fraction has a clear correlation to temperature in the reaction zone. Most of the data is clustered at high temperature region, which was expected for this data point in the flame. However, at low temperature, when a significant concentration of oxygen is present in the provolume, these measured water vapor mole fractions show a more spurious correlation, which we attributed to beating between nitrogen lines and oxygen lines employed in the measurements. One important capability of this technique is that we were able to acquire correlated data in time, so we can provide an assessment of the dynamics of the turbulent flame. So finally, to summarize, we have presented an innovative Cars diagnostic technique based on time-resolved signal dephasing, and we performed the proof of principle to detect water vapor in flames, right? And we performed the proof of principle in a laminar flame, where we acquire quantitative information of temperature, oxygen, hydrogen, and water. We also extend the capability of the technique to turbulent flames by performing single-shot water vapor measurements using a dual-probe polarization-sensitive coherent imaging spectrometer. For the future, we want to perform space-time correlated measurements using Cars line imaging, and we want to evaluate the feasibility of the current technique also in hydrocarbon flames, where other molecules such as CO2 are present in the probe. Thank you for your attention.